Good evening, ladies and gentlemen, and welcome to Chemistry in the Kitchen. I'm your host and head chef, Jacob. Today I'll be assisted by my sous chefs, Hannah and Sophie. Sophie, please tell everyone what we'll be making today.
Of course! Hello everyone! On today's episode of Chemistry in the Kitchen, we'll be making cupcakes!
But not just any cupcakes. We will be baking cupcakes using the fundamentals of stoichiometry. What that means is we will be looking at the ratios of what goes into baking the cupcakes and figuring out what ratios make the perfect cupcake. Baking is a lot like chemistry and uses chemistry fundamentals even though we don't realize it.
For today's control recipe, you will need plasticware for measuring, a muffin tray, a cup of flour, 3/4 of a cup of sugar, 2 teaspoons of baking powder, 1/4 of a cup of shortening, 1/4 a teaspoon of salt, 1/2 cup of milk, 1/2 teaspoon of vanilla, 2 eggs, frosting, and 3 cups of a good attitude.
For our other 2 recipes, which will be testing differing ratios, you will need 2 teaspoons of baking soda. In the recipes that are different from the control, one recipe will have 2 teaspoons of baking soda instead of baking powder, and one recipe will have no eggs added.
So what is stoichiometry? Let's hear what you had to say.
What's the definition of stoichiometry?
I don't even know what that is. Good question.
What's the definition of stoichiometry?
I've got honestly no clue. I couldn't tell you.
Can you spell it?
Can you say it again?
Stoichiometry.
STOKYOMETRY. Is that right?
David, pass the weed. Hey, show your ID to the camera. Pass the weed, David.
Stoichiometry.
Stoichiometry. That is a concept in chemistry where you are determining how many moles of one element equals moles of another element.
Yeah.
That's my guess.
As you can see, we need a refresher about stoichiometry. The actual definition of stoichiometry is the study of relationships and ratios between 2 or more substances undergoing a physical or chemical change.
Stoichiometry can also be used to convert particles, volumes, and moles to different units of measurement. This chart is a great tool to use when trying to convert from unit to unit. Look at the top left corner. When converting particles to another unit, you must divide the amount of moles of that particle by Avogadro's number. For mass, you must divide the grams given by the molar mass to find how many moles you have. For volume, you must divide what is given by 22.4 liters to again find the amount of moles you have. To convert, everything must be transferred to moles because when writing out a reaction, you use mole ratios in the reaction to convert. You can also just do simple mole-to-mole conversions.
Now that we know a little bit more about stoichiometry, let's use our chemistry concepts and bake.
First, we will make the batter for our control cupcake.
How important is it to add the correct amount of reactant in order for your reaction to occur? In today's episode, we're going to bake cupcakes and you're going to see the chemical reactions. More than one chemical reaction is going on when you're baking a cake. Try to predict what may happen if you vary the amount of reactants that you put in the cake. This relates to chemistry, because if you don't add the correct amount of chemical reactions before the reaction, the product may come out different or the reaction may not occur. Look at the different cake batters and how they are different.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, kryptonium, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium.
Now we will make the batter with baking soda substituted for baking powder.
Notice how the ratios of baking powder to cupcakes are different than the control.
Now we're going to make the last batch without eggs.
For this batch, notice how the ratio of eggs to cupcakes is different than the control.
Look at the different cake batters and how they are different. The mole of the reactant in the batter of one group will be different than the mole of a reactant in another. Now that we have them in the trays, let's put them in the oven. Gee, that's hot. While the cupcakes are baking, here are a few things to consider.
How important is it to add the correct amount of reactant in order for a reaction to occur? More than one chemical reaction is going on when you're baking a cake.
Try to predict what will happen with the varied amounts of reactants that we put in the cake.
This relates to chemistry because if you don't add the correct amount of chemical reactants before the reaction, the product might come out different, or the reaction might not occur. We will observe the way each cupcake looks and tastes after they are cooked and discuss how different ratios of ingredients cause different outcomes. Think about it and we'll give you the answers right after our break.
Two commonly used terms in stoichiometry problems are the limiting and excess reactant. The limiting reagent in a chemical reaction is a substance which is totally consumed when the chemical reaction is complete and determines the amount of product formed since the reaction cannot proceed further without it. The excess reactant is the reactant in a chemical reaction that remains when a reaction stops and does not limit the reaction.
4, 3, 2, 1.
Oh, you shouldn't let it keep beeping. Our cupcakes are finally done. Let's take a look. Here's our control. It looks perfect. And I'm sure it tastes great too. All thanks to stoichiometry. We have the perfect ratio of ingredients in our control. Cupcakes turned out. These were our cupcakes with baking soda instead of baking powder. They look more brown. The ratio for this one was similar to our control, but with a different chemical. So a different chemical reaction occurred. Let's look at that ratio one more time. Let's take a look at our third batch of cupcakes. These were our cupcakes without eggs. These appear to not have risen and look terrible. For this ratio, we were lacking an important ingredient that created different results for our chemical reaction in the cupcake formation.
Here are some more examples.
Let's take the balanced equation for the formation of water. Notice that this equation contains the lowest whole number coefficients possible. From this, we can garner exactly how many moles of hydrogen are needed to react with 1 mole of oxygen. In stoichiometry, we shift our unit from molecule to mole. According to this equation, we need 2 moles of hydrogen to react with 1 mole of oxygen. This is called the mole ratio. It is defined as the ratio of moles of one substance to the moles of another substance in a balanced equation. To determine the mole ratio between two substances, all you need to do is look at the balanced equation for the coefficients in front of the substances you are interested in. Let this be your guiding mantra for doing stoichiometry problems. The balanced equation for water has several mole ratios in it. There are 2 moles of H2 for every 1 mole O2. We will write the ratio as 2 moles H2 to 1 mole O2. There are 2 moles H2 for every 2 moles H2O. 2 moles H2 to 2 moles H2O. There is 1 mole O2 for every 2 moles H2O. 1 mole O2, 2 moles H2O. Why do we care about mole ratios so much? Mole ratios are the central step in performing stoichiometry because they allow us to convert moles of one substance to moles of another substance. Another balanced equation is the making of ammonia. N2 plus 3H2 reacts to form 2NH3. Pause the video right now and see if you can identify 3 mole ratios in this equation. Remember, look at the coefficients in the balanced equation. Here are 3 mole ratios. 1 mole N2 to 3 moles H2, 3 moles H2 to 2 moles NH3, 1 mole N2 to 2 moles NH3. If you expressed any of these ratios upside down from what was shown, like 3 moles H2 to 1 mole N2, you are still right. Nice.
Thanks guys for tuning in to Chemistry in the Kitchen. Let's take a quick look back at all we've learned today.
The definition of stoichiometry is the study of the relationships or ratios between 2 or more substances undergoing a physical or chemical change. We can convert from moles, grams, and particles using our chart. Stoichiometry is used in everyday things like cooking. Mole ratios are important to produce the best final product in the kitchen when baking.
Once your cupcakes have cooled down, enjoy!
And eat.
Thank you for joining us today for Chemistry in the Kitchen. I'm Jacob, your host. See you next time. Good evening, ladies and gentlemen, and welcome to Chemistry in the Kitchen. I'm your host, Jacob.
We're never gonna get warmed. Wait, let me fix that. I'm trying to do it. It's like in my eye.
Turn. Wait, y'all look intensely at the camera. Wait, get closer.
Are you tired of chemistry?
Yes.